good? Okay. So, advance, your first video, right? You guys been crying and crying and crying. So, again, just to recap what we did with the FRQs. You get FRQ 1, FRQ 2 correct, that's 30%. You need 42% of pass, so like 4 or 5 questions on the multiple choice. So how do you do this one on problem number 1? So on part A, literally, part A, right? It's asking here, determine the state of and state the angular velocity, right? Angular velocity, this is this W, right? We'll call it W. Equals to theta over t, right? So then when you think about this, you're talking about a Ferris wheel. So if you recall the unit circle, and you do a whole revolution around the unit circle, in radians that's called 2 pi, right? So here, my theta is basically doing 1 revolution over, here they gave us what? 60 seconds. So 60 seconds, right? But now, I need to get rid of the revolutions. So instead of revolutions, I'm gonna put radians. So I'm gonna put 1 revolution at the bottom. So this and this simplify, and then over here you're gonna put 2 pi radian. So now, what does that give you? Well, that gives you 2 pi radian over 60 seconds. And that is literally your answer. Just leave it like that. Okay, determine the state. I'll be glad if I see this just like that. You want to be fancy, use a calculator, right? Or simplify, right? 2 pi over 60 is basically pi over 30, which is just 0.1047. And again, units, radians over seconds. Cool, cool. So that's literally part A. What about part B? So for part B, which is over here, right? All you're doing is now saying, find the, where is it? Assuming the Ferris wheel moves at a constant rate, find and state the rider's linear velocity, right? So linear velocity is gonna be, well, this, right? This is equal to, and basically the same thing as before. If you notice this right here, theta over time, that's this right here. Alright, so we already have that. Radius. Radius is what? Well, diameter is 90, so take half of that. Radius equals to 45 feet. So plug in. So I have 45 feet times 2 pi over 60 seconds. Right, I misspelled the seconds. Right, radians. Right, 45 times 2, 90 times the pi over the 60. Right, so you're left with feet on top, seconds on the bottom. And that is literally your answer. If you want to simplify it, you get 3 pi over 2, right? Or this is equal more or less to 4.712 feet per second. ¿Qué más quieren? ¿Qué más quieren? This is literally 15% right there. So on part A, theta over t, and on part B, theta over t, but on top you're multiplying theta times the r, which is the radius. So now, if we keep on going, and if we keep on going, this could help me out here, right? This could help me out here and make this look so much pretty, right? I went over another one, right? So on this one, let me erase this real quick. So this is a second FRQ. Literally. Y'all know how easy this is? How simple this is? If you look at part A, verify that the initial position of the rocket is at the origin. When you think about origin, you're thinking 0, 0. You get a point, that's literally your answer. The origin is 0, 0, right? But you have to show me your work, right? You need to verify it. So now, x is 0, y is 0. That means t, which represents x, is 0. So 0 here, 0 here, 0 here. These two that act as the output, they're also 0. So this is basically, you need to show me this for part A, right? So this is part A. So literally you're gonna have 0 equals 60 times cosine 45 degrees times 0. And you're also gonna have 0 equals 60 times sine 45 degrees times 0. Did I plug in 0 for t? 0 t here. Also, look, I forgot this section right here. So minus 16 times 0 squared. That is literally all you have to do. Okay, let's get it. Okay, let's get it. Alright? So now, it says here, find the maximum height of the rocket. So, when it reaches the maximum, right? So, which one should I use? X of t or y of t? Well, when I think of maximum, I'm going up and down. So I'm pretty sure that for part B, I need to use this equation right here. So now, if I try to graph this just the way it gives to me, it won't work because of t, right? So in order to graph this, I need to switch that t to an x. So when I go to the calculator, right, I need to make sure that I go to the graph. I need to make sure that my calculator is in degrees, right? If it's in radians, just press on it, right? So then what do I have? Well, I have 60 times sine of 45 degrees, right? Times x minus 16 times x, and you square it, right? Should be it. And there it is. So now from here, I need to find the maximum. So in order to trace this, I'm gonna press menu. You're gonna press 5. You're gonna press 1. Right? But let me just erase this real quick. So I go over here, go to the right, look for the maximum. Maximum is what? What is it? Ooh, I forgot to erase a small portion. So maximum is gonna be 28.13. This is your max right here. Alright? That is literally it. So if I go back, the answer, oh, we got it right on the spot. You see that? Part B. So find the maximum. The maximum, you look at the y. So 28.13. And there you have it. The last portion, which is part C, literally, it tells you, determine how much time it takes for the rocket to start and hit the ground. So again, time, you're looking at your input. But I'm not going to use this one. What I have to do is go back to my graph. And literally, you already have the tracer open. So start it at 0. Alright? So if I started at 0, if you started at 0, right, and you keep on going, you reach the maximum, rocket's going up, and then what goes up must come down. And there it is. So here, my answer is 2.652. That is how long it takes in seconds. This right here is literally a super duper small decimal, but literally just round it to 0. So my answer for part C is t equals 2.652 seconds. And there you go. That is basically it. So again, you get the FRQ correct, that's 30%. You need 42 to pass. So please don't botch this one. But knowing you guys, you will, since you guys always try to prove me wrong. And let's call it a day.